Okay, let me start. So, in the previous two lectures, we discussed about a simple wire, a resistor, a capacitor, an inductor. And we have seen at RF frequencies, especially, or AC or high frequencies, unlike in basic electronics, your resistor changes its value a lot. It may become like a 0 ohm or a short circuit. And then we discussed about capacitor. It may start behaving like an inductor. And we have seen the equivalent circuit also. And similarly, the inductor may behave like a capacitor. So that is a very serious problem. So what are those parameters that we have to look for in either of these? So that we discussed. And we have seen that all these are playing a very important role in our circuit design, system design. But if you see the today's laptops, which is a 3 gigahertz typical processor, or a PCBs and everything, you will not find any LNCs. So where they have gone? Either they have vanished. No, they have not vanished. They have taken a different avatar, as we'll understand in this lecture series. So that means you can say that there is a huge demand of such engineers, because everything is now at 1 gigahertz and beyond, and there those basic electronics concepts don't work. And we've also seen that everything is now in terms of impedance, because it changes the value with the frequency. And multimeters are not useful because multimeter measures at the DC or the low frequency. So we have to find some other equipment to measure this RLC. So just like we know, the applications of capacitor is used in filter, LC filters, oscillator, where the resonant frequency is given by F equal to 1 by 2 pi under root of LC. In DC block, similarly, just to finish that part, I can say your applications of L, which is inductor, what could be the one? So one could be, as I said, could be in terms of LC filter. Okay. We are also using in terms of oscillator, where the resonant frequency is given as F equal to 1 by 2 pi under root of LC. Okay. We have seen the resonance is also taking place when LNC circuit are there in RLC equivalent circuit. It is also used for the delay, because delay introduces phase change, and here we can't introduce the phase. We have to also take into account the phase part. Like in basic electronics, you must have done an experiment. Suppose I give a 5 millivolt signal amplified by 10 times, let's say using an amplifier, you get 50 millivolt. So that is something which you have learned in the basic electronics. But in RF electronics or high frequency electronics, we speak in this language 5 millivolt 0 degree. That means the phase is important. But you will get here is 550 millivolt. And because of the length, there is a length of the circuit. And the more the distance, more the time taken, more the delay. So this will introduce delay, and delay will introduce a phase change. So I got something like, let's say I get 30 degree. And we have to compensate for this 30 degree. So that is also when you to compensate or introduce delay, we use, so I have to use a delay of 230 degree to get almost 360 degree or 0 degree at the output. And that can be possible by introducing an extra line length or so. Also another application which is very, very important also from the RF point of view, is RF choke. Just like a capacitor is used RF choke. Just like we have seen that a capacitor used for a DC block, your inductor will use RF choke. It can be used. That means it allows DC to pass and through, and doesn't allow RF or AC to pass through. So it is the opposite of what we say for a capacitor DC block. Choke is also used for the blocking, but here we use the word more commonly used choke, like you must have seen the tube-like choke and so on. So basically they are all inductors and so on. Now moving further, so these are the various applications which could be possible, especially when we do the experiment in high frequency circuit, we use something what we call a very interesting concept, bias T. T, as you know, is in the form of a T-shirt, something like this. So basically what we do here, we have to, suppose I am testing an amplifier. And for amplifier, I have to give a DC bias also, as you must have seen. And we give a input here and we get the output here. And this is, now my input is earlier a low frequency signal, but now it is a high frequency signal. So basically, if I have a high frequency signal at the input and DC, which is a very, very low frequency, it will damage my amplifiers and the instruments also. So what we do here, we use what we call the concept of bias T. So what is this bias T? It is something like this. It is a system of this type. So it is in the form of a T. There is an inductor and so we use something a T is like this. So basically T is something like this, a system where I have an inductor and a capacitor like this, and this is the one. So this is the L, this is the C. It will act as a DC block, as we know the application. Here we use as a RF choke. Some static problem. I think from next Monday, we'll be having mostly the hybrid classes, so this problem will not be there. So this is the RF choke. So what we do here, when I have to use this, I give DC bias here rather than directly giving. And so your inductor will allow DC to pass through. And I give my RF source, which is a high frequency source, which is the input to the amplifier like this. And then it goes to the amplifier. So our system becomes something like this, and then I measure this output. Now what will happen here? RF is a high frequency source, so it will pass through capacitor. Capacitor will not allow DC to pass through. So if any DC will not comes here, it will not come to my signal source here, and it will protect my instrument. Similarly, a high frequency instrument will not my DC power supply. So this is my DC power supply, so it will not damage, because one is high frequency and other is low frequency. Earlier, both were low frequency. Your DC power supply was low frequency, and your source was also, input was also low frequency. So there was no chance of damaging the instrument. But here, if a high frequency signal goes to the low frequency DC power supply, or a DC goes to the high frequency source, they may damage the instruments. And these instruments are very, very costly. A typical RF source, which we have in our RF lab, which you will be using as an elective in third or fourth year, as I told you. So then you will find that one RF source instrument costs around 30 or 40 low signal function generators, which you use in basic electronics. So this is something used as a precaution. We always used bias T, because this is DC is a low frequency, and this is at high frequency. So one frequency should not damage the other one. Now, what are the solutions for this? So basically, if you find for the resistors, we have what we call the chip resistors, because we have seen the resistors are giving the problem because there are two leads. And when the two leads are there, inductor is there, capacitor is there, and so on. So basically, we nowadays we used chip resistors which don't have any leads. You will find they are very small in size. So basically, it is in the form of a chip, something like this, very small in size. So there is a chip, and here there is a metal part, and here there is a metal part. Okay, so this is the length and this is the width, and this is, as I told you, metal. So it is like you are cutting away the leads. So your parasitics of L and C are removed, and they are very small in size. So for the chip resistors, we use this thing, and they are of various values, 20 ohm, 100 ohms, and so on. So basically, they are decided by the size code, and size code means what is the length in mils, as I said, and what is the width in mils. We have already seen mils is what? It is 1,000 of an inch. So they are available in various codes, like we have American wire gauge system or standard wire gauge system, something like this: 04, 02, 06, 03, 08, 05, 12, 06, 12, 18. What it means, its length is 40 mils and its width is 20 mils. Its length is 60 mils. Its length width is 30 mils. This is 80 and 50. So that is like a code value, because they are very small in size. You can't measure using the scale or something like that. And this is 120 by 180. So various standard codes. Obviously, the smaller the size, the costlier is the chip, because your parasitics will be reduced. Because if the smaller is the size, the distance between the two metals also gives me the stray capacitance. Lead capacitance, lead inductance and resistance we have ignored now, because there is no leads. But this is something like still there is a distance, and this distance will be small in a smaller chip, and I will get a less stray capacitance, as we have seen here. So these are very popular. And if you find now in most of these things, we are having a very, very small chips in our systems and so on. Also, if you see here, L and C are, as I told you, are used in the printed form. They have taken a different avatar, which will understand how they have taken in a different avatar. So basically, when you use L and C, they look like with different designs. You will find a design something like this. There is a line here, there is a line here, there is a line here. So this is metal, this is metal, this is metal. So basically it is nothing. It gives me an inductor, it gives me an inductor, it gives me an inductor. Two metals separated by a capacitor gives me a dielectric. Two metals separated by a dielectric gives me capacitor. So basically if I see its equivalent circuit, it will be something like a LC filter. 1, 2, and 3. So basically I am replacing my simple inductor and capacitor by line lengths. But what should be the line length? Because as I said, your inductor could be take any value from 0 to infinite Henry. Similarly, your capacitor can take value from 0 to infinite Farad. So what type of line we should use, how much length we should use, whether we use a short circuit line, that means it is short circuited, or an open circuited line, and so on. So you will find these type of the designs in our circuits or mobile phone circuits, your PCBs of the laptop or PCBs of this thing. You will find something like a design like this. This is also an inductor, because it is simply a metal which is formed in the form of a this thing in the coil. Because sometimes the distances are very small. We have to keep miniaturization plays a very important role nowadays. So this is the length, but I've actually put it in a toroidal form, or a form like this, meander lines, what we call and then it can be folded. So basically the line length decides this thing. So you will find, so this may behave like an inductor. So these are some of the things which we are going to discuss, how these things are designed. So having learned that, what we call the inductor, capacitor, resistor, wire. Now we talk about transmission line. Now that is very, very important concept, as I told you, from various examination point of view. Like for PSUs, you have to give the gate examination. So this next the few lectures I'm talking about that play a very, very, very important role there. Or civil service examination, if you're taking these subjects, EC or something like that. So that plays a very, very important role. The transmission line concept. As I said, it is very, very old concept, but it is still being used, because we are using the transmission line like a copper cable, which is coming for connecting our antenna to a TV, or a landline connection, or different forms of transmission line, or the various forms of transmission line. So basically, what is the difference between a wire and a transmission line? So as I said, it is an extension of what we have learned. So we'll talk about transmission line. So transmission line is basically a two-wire. If you see your black copper cable, which is connecting your TV to the antenna or a landline phone, you will find that there is a center conductor, which is a metal, outer which there is a jacket of black color, which is like a protective shield. But within the jacket, there is another mesh of wire. So that is another conductor. And between these two conductors, you will find there is a white material, which is a dielectric or perspex. So basically, if you see your cable which you are familiar with, there is a center conductor which is of metal, and there, if you find there is some mesh of wire here, so this is also metal, and then there is a something like a white color which could be your perspex or Teflon, which is basically your dielectric. So basically, a transmission line is different from a single wire. Single wire is a single wire which has a equivalent circuit of simply L and R. R is the material of the wire. But here, if you find after that there is a protective covering, you will find there is a black color protective covering just to protect the your plastic covering. It is to cable. Okay, so this is the metal which is you normally use a center conductor, and it is we give the signal here, and this acts like a ground. Okay, so this is the something like which is a very common type of the line. So transmission line is, I would say, a two conductor line separated by a dielectric, or even it could be two wires which we normally twist. So those are also extended transmission line, one for the signal, one for the ground, and the dielectric could be taken as air between them. So separated by a dielectric, and dielectric could be air. So basically, it is important that we have separate lines. And we will talk about some of these lines later on. Nowadays, they have come in a printed form also. So, so this is the something which you are aware of. So this is, as I told you, wire is a single conductor. So what we learned about the wire, so it is a dual conductor separated by a dielectric. So what is the, again, if I have to understand this, we have to start with I'm not using equivalent circuit of the transmission line. I will be using this word TX, which is quite common for transmission. Okay. I'm not able to use the top half. So basically what happens here, equivalent circuit of the transmission line, how I can represent. Now there is a upper wire. Okay. So upper wire has got some resistance, some inductance, and so on. And so this is like this. So this is one wire. This is another wire, which also could be represented by R and L. But I'm just taking in one of these cases. But it is also a R and L here. Okay. Now they are separated by a dielectric. So if they are separated by a dielectric, they have a capacitance because of that. And also there is what we call the conductance, G. Let me understand the significance of everything. Just so we know the significance of L, because R is due to the resistance of the conductor. So there is a dielectric. So it represents the dielectric. And wire, L and R, and similarly L and R we can take in the ground, but just for simplicity. So this becomes my equivalent circuit. So let's understand the significance of each element. So here R is basically due to the material of the wire, which you have understood, or I would say conductor, single conductor. L is basically, as we have seen, wire consists of R and L. It represents the magnetic flux, okay, which is generated by the current, because we have to pass a current or voltage on the transmission line. So generated by the current on the transmission line. C is basically, we have understood, it is a capacitance due to dielectric between two conductors or wires. Okay, I use the word between. And then we have the G. So it has got the unit of Henry, this has got the units of Henry, this has got the units of Farad, and this is what we call conductance. And conductance is here is not the reciprocal of resistance. Okay, though it has got the unit of ohm inverse or mho or Siemens, whatever you call, or sometimes it is written as. So here G is not equal to 1 by R. It is not equal to G is equal to 1 by R. But G is basically, it represents the coupling current between two conductors. And I will explain just now. First I will write down between two conductors, because dielectric is not a perfect conductor. It has got some finite conductivity. So it is not a perfect insulator. It is not a perfect conductor. So that means there is some conductance, and because of that there is some conductivity. Okay, and some current may leak from one conductor which is used for the ground, or from the signal to the conductor which is taken as a ground. So here we give one of the signal here. So we normally apply the signal here, and this we take as a ground. Okay. So what happens here, because this dielectric is not a perfect conductor, not a perfect insulator, that means it has some finite conductivity of its own, some finite conductivity. And because of which there could be some leakage current from the upper wire to the lower wire. That means from the signal to the ground. And this gives rise to what we call the conductance. So it is not equal to 1 by R. So it is sort of a leakage current. And that is the reason why, if you notice in the landline phones, unlike in the wireless phone or mobile phone, they use, suppose I am calling one person, sometimes I overhear the other person also. Okay. That means some other call is taking place, and I am also able to hear that. Why this has taken place? Because your conductive leakage current becomes very high and so on. And that is the reason which gives rise to the crosstalk or something like that, which we sometimes overhear in the case of a cable. So as I said, all these things are important. Landline was there, will be there, continue to be there. Okay. And similarly, your wireless was there, is there, will be there. Fiber optic was there, is there, will be there. So all. In fact, as I told you in my first lecture also, that when I'm speaking to you, I may be speaking from my mobile phone. It may be going through a wireless medium, that is a free space. Finally, at your end, you may be having a fiber connectivity. And so every form of the communication is involved, or you may be having a landline phone. So so all forms of communication are going to be there. Another thing to be noticed here is this R, L, G, C, they are not fixed values, not fixed, or what we call the not lumped. We use the word lumped, as I told you in my first lecture for this one. Means they are distributed in nature, because at every point on the line, its value changes. Suppose I'm measuring my resistor at this point A, it may be having a different value. At B, it may be having a different value. C, it may be having a different value. D, because as I said, the length will be there, or because of which there could be delay, there could be phase. So everything would change. So here we say they are distributed in nature. So when they are distributed in nature, your values of RLGC are expressed in terms of ohms per unit length, millihenry, Henry per unit length, whatever you call, Siemens per unit length. Length could be centimeter, millimeter, and farad per unit length. Okay, this we express as F, Siemens, Henry, or millihenry, microhenry. And because of this, as I said, because R has become an impedance, C has become an impedance, L has become an impedance, they are not simply RLC. So as I told you earlier, V is not equal to IR. KVL is not valid. KCL is not valid. So how to analyze a transmission line? And my transmission line is not a small line. It basically runs from cable, from under the sea, from one country to the other country. So it is not a small line. And I'm noticing that if I am having the equivalent circuit of transmission line, which has RLGC, their value changes at every point because of the large length and so on, and they are distributed in nature. So how to solve such problems? So how to analyze a transmission line? Now here it becomes a little mathematical. From now on, just most of the things will become a bit mathematical, but I assume that you don't know anything. So I try to put in a simple fashion. But yes, if I give you simply the formula, which normally is the trend in the examination when we go for the MCQ type or short answer type, so that will not help unless you understand how these things come. And especially in the transmission line, this is very important to have some mathematical derivation. Just if I give you the formula, it is something, as I told you earlier, that if I give you a bottle of glucose water right now, when you're sitting idle, you won't appreciate it. But when you run for 200 meters, you will appreciate that bottle of the glucose water. So similarly here, if I have to understand the concepts, I have to do some slightly mathematical analysis, and which I'll put in a very simple way. Okay. Initial first two slides are the analysis will be a bit difficult, but it is not that difficult. But in continuing classes, it will be very, very easy. It will not. But yes, I would appreciate, rather than giving the formula, I will devote my time in this thing, and that is also equally important. So how to analyze my transmission line? So I go for analysis of transmission line. How to start that? So basically, to do this, because our transmission line is very, very long, and I can't apply KVL, KCL, Ohm's law, and so on. But still, I have to use that knowledge. How to use that knowledge? So what we do here, we divide the transmission line of length, let's say L, into a number of small sections, infinitesimally small. Infinitesimally small means infinite sections of very, very small length, into number of infinitesimally small sections. So that means many sections of very small length of length delta Z. Okay. So basically, number of small sections n of length delta Z. So basically, where my n tends to infinity and delta Z tends to 0. So what I'm doing here, because my line is so much different and my behavior of the line changes at every point, as I made you understand this thing, very important. So I divide to understand this transmission line, and whatever the concepts which you have learned, KVL, KCL, I wish to apply here, because without those laws, I can't move further. Those laws are still important, as I said. So basic electronics is still important to understand this RF electronics, transmission line theory, and so on. So what we do here, I divide my transmission line into n number of small sections, n tending to infinity, and each section is of very small distance delta Z, and the Z tending to 0. Okay. So what I do here, I take a small section. So one small section will look like this. Okay. So this is one small section I am taking. Okay. One small section I am taking of length, as I said, delta Z. Okay. So here I've got Z, and here I've got Z plus delta Z. Okay. And as I said, delta Z, it is basically tending to 0. And there are n sections. So I put it like this. So there are many sections here. So n sections, n tending to infinity. But I'm taking only one section. Now, if I apply a voltage, now here we don't apply a simple voltage. Here it is a time dependent. Okay, because my voltage also changes, because at every point my behavior of resistor is changing. So let's say this is the voltage at ZT. Okay, and the voltage that I get here is V, Z plus delta Z at some other instant T, same instant. But because of it is a small distance, I am assuming that very small. So it becomes VZ plus delta ZT. And the current that passes through this is, I could say, just to make clear, IZT. Just write it very clearly here. Small letters we understood, it is basically for the AC voltages, AC current. So it is IZT, And my current here becomes here is I z plus delta z t. Okay. Now here, what is the advantage I'm getting? Because I'm at every value, my R, L, C, G are changing. But if I've taken a very, very small section, that means in that small section, my R, L, C, and Z are constant. And that will make my task very easy. And because earlier my units were what we call the R, this ohms per unit length, inductance per unit length, capacitor per unit length. Now I made it lumped values by multiplying with delta Z, R delta Z, L delta Z, G delta Z, C delta Z. So my values have now become from per unit length to a fixed value. Okay. So this becomes L delta Z. This becomes R delta Z. And as I told you here, R has got the units of, I move to the next slide. R has got the units of ohms per unit length. Just to give an example, because it is distributed earlier, now I made it a lumped value, R delta Z. So your unit becomes ohms per unit length into length. And that means it is ohms. So it becomes a fixed value or lumped value. Now that means I can now apply my KVL, KCL, and so on. Okay, so we'll now apply. So I will go one by one. So if I apply, let's start with, first I will apply KVL. KVL is nothing, if you don't know, it is a loop equation. Okay, Kirchhoff's voltage law. So this becomes my Kirchhoff's voltage law. Again, if you don't know. So it is, I think that you must have learned it. So if I apply the KVL loop equation, which we call, okay, what it means? It means sum of voltages in a loop is equal to 0. That is my KVL. So in this case, if I applied the KVL in the previous circuit, okay, my equation will become like this, which becomes very easy. VZT minus R delta Z, okay, into IZT. So that has got the unit of voltage, R into I. Again, it has got the unit of voltage, and similarly, minus L delta Z into del I by del T, ZT, that you must have been knowing in basic electronics, how we write, and it becomes my total equation, Vz plus delta Z at time T. So when we write this VZT, it means instantaneous voltage at Z, okay, which was my starting point. If you see this circuit, this is my Z. And this is my Z plus delta Z. That means the instantaneous voltage at Z plus delta Z T is given by Vz plus delta Z T. So if I apply the voltage KVL here, that means the sum of voltages in a loop is equal to 0. My equation becomes like this. So if you see, this is a unit of voltage, this is another is a voltage, output is the voltage, again this is the in terms of the voltage. So this becomes my simple equation. Nothing great, very simple. Here for your reference, so that you don't refer to any other book, I would say where V is at T, which I just said, it is the instantaneous, because the time is there, as we have seen in the AM and FM, instantaneous word we use when the time concept is here. And here my time concept is very important, because with time there is a delay and so on. And Vz plus delta Zt is equal to instantaneous voltage at Z plus delta Z. Okay, so this is done. Now, what I do here, the equation that I got it, that is the first equation, I rearrange this equation and dividing by delta Z. Throughout I divide by delta Z and combining V terms together, because there are two V terms, one is R term, one is L term. So V terms, we keep it together. What we get? So nothing great. It is just simply I'm dividing throughout by delta Z, bringing the V terms together, say on the left hand side, other terms on the right hand side. So this equation becomes like this: minus V Z plus delta Z T minus V Z T over delta Z is equal to R I Z T. So that is also voltage term plus L del I by del T Z T. So nothing great. Brought the V terms together on the left hand side, other terms on the right hand side, dividing throughout by delta Z. That's all. So I got this expression. Okay, fine. We'll move in the next slide. Now what we do here, how to solve? As I said, we are assuming delta Z2 is going to 0. Okay, so I have to apply that limit. So in limit, which we know, delta Z tending to 0, here you must be knowing that here in this case, your difference goes to differential. So what we get here is, if I apply this limit, delta Z tend to 0, what we get here is minus del V Z T over del Z is equal to R I Z T plus L delta I by delta T Z T. So this I mark the equation which is important to us. Let's mark this equation as 1. My equation numbers, irrespective of the lectures, will continue throughout. So it will be like a book you are reading. So if I am having starting one equation number 1 here, and I have to mark another equation, my next lecture, it will start with 2, 3, 4, and my next lecture, it could be 5, 6, 7. So it is like a uniform book type of things you are reading. So that is the equation that we got it in terms of a differential equation. When we applied the limit delta Z tend to 0, your difference, which is the Greek delta, triangular one, it becomes goes to the differential. So that was when we applied the KVL. Now, similarly, we apply applying KCL. KCL is, as I told you, it is Kirchhoff's current law, and that is always applied to a node N. Okay. And what is this? KCL is sum of currents. That was a loop equation. It is a node equation. So into a node, which we defined as, let's say, N is equal to 0. So where is my node N? So first I will take this circuit, which is in my previous slide. So I have to mark a node. And here my node, I am marking with this node N. So the sum of currents entering into a node is equal to 0. So this is my node. So in this case, if I have to apply the KCL, just like we did for the KVL in this previous case, which I marked as 1 here, applying KVL. Now we'll go for applying the next step is some static charges problem is coming. Now here, what is that? Sum of currents. So my equation, just like we have done in this KVL, it becomes IZT, which is a current equation, minus G delta Z, which is the conductance. That means 1 by R multiplied by VZ plus delta ZT. So that is becomes my, again, if you see, it becomes a current equation, voltage by 1 by R. G is, though it is not 1 by R here, but G is a conductance, so it is got the same units, minus C delta Z. Previously we had inductors, now we have zeta VZ plus ZT over delta T is equal to IZ plus delta Z T, just like we have for the case here. So this is a minus. So this becomes my, when I applied the KCL to the node N. That means the sum of currents into a node is equal to 0. So if you see everywhere I'm writing about the current, first term is current, second, third, all these terms are with respect to the current. Again, as we have done in the previous case, I rearrange and dividing by delta Z. And rearranging means combining items together, combining items like we had the B terms there. And what we get, and if I put the limit delta Z tending to 0 also, which is the one we have done last time also. So we get something, an equation like this, and the same line, minus del I zt over del z. So here I combine two steps into one. That means I rearrange all the terms by bringing items together, dividing throughout by delta z, and applying the limit delta z to 0. That means difference goes to differential. I get the same replica of the previous equation, but it is more a KCL. That means C delta P by delta T ZT. Okay. So this I am marking as equation number 2. So 1 and 2, what we have got are general transmission line equations. They are very general transmission line equations, or because, as I said, this is very old concept, but it's still being used in whatever system we are designing. Even a system like your PCB is also having a line connecting one system, one component to other component. A transmission line is connecting, a printed line is connecting to them. So there also how much length we should use and also so that my system does not give undesired results. Okay, when I'm so even my printed line on a PCB, as I said, it could behave like an inductor or a capacitor, but containing, which is joining the two components, also has to follow these principles, which we are going to discuss. And this is so common that they are also called the telegrapher's concept. I think the telegrapher is something which is the earliest form of the communication system. Okay, the most common form of the communication system was people speaking in a loud voice or through the pigeons. But in reality, the electronic communication system, which we typically heard of nowadays, we don't know, it is called a telegraph and telegrapher's equation. So these equations are the general transmission line equations, also known as telegrapher's equation. So this is such an old concept, but still being valid when I'm designing a PCB for high frequencies, for say laptop or for my mobile phone or for my TV or something like that. Okay. Now, we have to solve these equations. Okay. Now here, it is a time-dependent equations. Okay. And you must have learned when we have a harmonic time dependence, that harmonic means the frequency or time concept and so on, we need to use the phasors concept. And I think you must be knowing, but I will explain to you what it means. So basically, this is today I'm not able to use full of my. So I say for harmonic time dependence equations like this, we use what we call a phasor concept, which will simplify our phasors. What it does, it simplifies the transmission line equations or any equation which is in the differential form. They are partial differential forms. So to ordinary differential equations, because we know ordinary differential equations very well. And this is the partial differential equations, del by del t and so on. So if we have the harmonic time dependence, we use the concept of phasors reference. So what is this phasors? So suppose I have a sine or cosine reference. Let's say I have a cosine reference. Okay. what we do, this is the concept of phasor. We write VZT, which is like a time-dependent parameter, as a real part of capital VZ E J omega t. So this is the how we write. And similarly, I could write, basically it will make my life simple, because instead of partial differential equations, we can get the differential equations, which you must have learned in the calculus also. So it is IZ E J omega t. So I got these 3 and 4. 1 and 2 were the simple KVL and KCL equations, which we applied the limit delta z tending to 0. So where my difference goes to differential, partial differential. Now I use the concept of phasors to make it to a ordinary differential equation. So let's mark this 3 and 4. So in my 1 and 2, these two expressions are there, VZT and IZT. So if I substitute 3 and 4 in 1 and 2, so substituting 3 and 4 in 1 and 2, we get ordinary differential equations. So that is the beauty of this concept, which you must have learned. And you can look into the Google and I think no any communication system books, but any calculus book or something like that. So my differential equation becomes simple like this: minus dvz by dz is equal to r plus j omega l I z. So I might write it very clearly. These are all dz. So that becomes my equation number 5. So I highlight it. And similarly, simultaneously, I'm doing for the voltage and current also. Diz by dz is equal to g plus j omega c into vz. So I got 5 and 6. Now, major thing is that now once we come to the differential equation, it becomes very easy. So these equations in 5 and 6, what are these equations? So these equations 5 and 6 are time harmonic transmission line equations. Okay, simple ordinary differential equations. But the problem is that now I see basically what is my aim. I have a big transmission line. At every point, my R, L, C are changing, they are distributed. So I've taken a small section to assume that everything is constant. So my units of R, which were earlier ohms per unit length, I multiplied by delta Z, that means the length, to get the fixed values. Now, because these values are changing, R, L, C are changing throughout my transmission line, the entire transmission line, at every point my voltage is changing, at every point my current is changing. So my aim is to find how the voltage is changing at every point on the transmission line and how the current is changing at every point on the transmission line. At basic electronics level or the low frequency electronics level, if you give 5 volt signal, you will always get that 5 volt output, despite how big is your cable or something like that, or whatever current you are expecting, that current you will get. Here, as I said, because this introduces delay and other thing, transmission line is also having an equivalent circuit. R, L, G, C are involved. So at every point, my voltage is changing. At every point, my current is changing. So what is my aim? What I am doing here, when I'm doing the analysis of the transmission line, what actually I'm doing? I am interested how to compute VZ and aim. So our aim is basically to compute VZ and IZ. And I got VZ and I dvz, simple differential equations, so I can solve it. Okay. But so I have to compute VZ and IZ from equations 5 and 6. Okay, how my voltage is varying, because I also have to understand how my voltage is varying and how my current is varying. So here at high frequency electronics, when I have to pick a cable, even for connecting a simple this thing, I have to very cautiously use the length and all those things, because it may change the entire parameter if I use a slightly bigger length, smaller length, or something like that. Okay, so that we'll see later on. But basically, our aim is to find out how my voltage is varying along the line, how my current is varying along the line. Now, if you see these equations 5 and 6 again, they are simple dvz by dz or diz by dz. So I can find out very easily. But the problem is that here my V and I are coupled. In my equation number 5, which is for dvz by z, On the right hand side is iz. And in the equation number 6, if I have diz by dz, and there on the right hand side we have vz. So basically, another problem I found that yes, it is not so simple. Here my equations v and I are coupled. So first we have to find the following solution for that. So in equations 5 and 6, what you notice, your v and I are coupled. So first we have to decouple. Then only I can solve for that parameter vz. If I'm solving for dvz by dz, by simply say integrating, but I have a on the right hand side is iz. And similarly for the other. So what we do, how to solve this? To solve this such a way where my equations are coupled. So what we do here, we take d by dz of one of the equation. Let's say one equation we start with it. Let's say I pick equation number 6 and substitute into another equation. And what is my another equation is, which is number 5. So pick one of these equations, say 5, take the d by dz of that equation and substitute into the another equation. So I've taken, let's say, picked the equation number 6. I will take the d by z of that equation and substitute into 5. Okay, let's see. So I pick this equation. I take the d by dz of that equation. So it becomes d square iz by dz square is equal to, I will just go back to the equation number 6 again to just show to that, d bz by dz. Okay. So just for your reference, I picked this equation number 5. Okay. I took the, number 6. I took the d by dz of this equation. So it becomes d square iz by dz square, g plus j omega c, dvz by dz. Okay. Now I substitute dvz by dz, which I got it, into equation number 5, where it's already there. So it will help me in decoupling. And that's how we decouple. Let's see how to go for that. So just give me 1 minute. So I got this equation. Fine. So d square iz by dz square is equal to this one. Okay. And substitute into another equation. Fine. So let's substitute. So first we have to find dvz by dz. So it means from this equation I get dvz by dz. Okay. Then we substitute minus d square. Sorry. So nothing great. If you see here in the previous equation, I got this. So I'm now finding dvz by dz. So it becomes d square dz by dz square over g plus j omega c. Okay. Okay. So I got this. This is minus sign here. Now, if you notice here, this is minus sign here. Okay. So in this equation also, I got a minus sign here. Okay. And I got this. Okay. So dvz by z. So therefore, substituting above in 5. We started with 6 and substituting 5, we'll get, what I get here is minus r plus j omega l iz is equal to minus d square iz by dz square g plus j omega c. Okay. If you see here, I recall that equation number 5 again for your reference here. So I replace this left hand side minus dvz by dz by minus d square iz by dz square over g plus omega c, and right hand side remains like that. Okay. So I go back to that. Each step is there for you. So this becomes like this. Okay. So if I substitute above in 5, I got this expression. Okay. Now if you see, my things have become very simple. I got a decoupled equation. D square Iz by dz square minus r plus j omega L g plus j omega c into Iz is equal to 0. So my equation has become decoupled. That is Iz only. Okay. It has become. Earlier it was I and V were there. Now it is I and I. Though it has become a d square by dz. So I can write down this as d square Iz by minus gamma square Iz is equal to 0. So we are introducing various parameters also simultaneously by which a transmission line is characterized. This I mark as 7, where I am defining very important parameters for a transmission line. Gamma square is equal to R plus j omega L into G plus j omega C, or gamma is equal to under root of R plus j omega L G plus j omega C. So this parameter I'm defining gamma as like this. Okay. This gamma, I will explain the concept, but I replace this parameter R plus j omega L G plus j omega C as gamma square. That is, but we'll explain the concept right now. Similarly, if I start with the equation 6, previously what we have done, we started with the equation 6 and substitute into another equation 5. So similarly, if we have done the other way around, if we take d by dz of 5 and substitute in 6. Last time we have taken 6 and 5. Okay. So what we'll get? We get on the same line. So we are not doing that. But on the same thing, we get a different equation, which is what we call something like this. D square Vz by dz square is equal to or minus gamma square Iz. Oh, sorry. Okay. Okay. So I got this equation. So basically what we found that here, if I start with the 5 and substitute in 6, or start with take the dz of 6 and substitute in 5, I got decoupled equation. So this is a decoupled equation in terms of V, and this is number 7 was in terms of the A. And I introduced a parameter which is called the gamma square or gamma. This gamma, if you see, are dependent upon the frequency omega, as we see here, 2 pi f, and also depends upon all the 4 parameters R, L, G, C, which are the equivalent circuit of a transmission line. And this parameter is what we call a propagation constant. Unit is expressed in terms of per unit length, say per meter or so. That means how my signal propagates in a line. So that is very important. When we consider a transmission line and give a signal, we have to know 2 things. How much the signal attenuates. Kitna wo attenuate ho gaya? Obviously, it depends upon these RLGC also, because R is a lossy material and all those parameters and so on. And the other thing is how the signal propagates, at what velocity it is propagating and so on. All these things are equally important. Okay. So this particular parameter, which we are just now bring into the picture very first parameter, gamma. It is a propagation constant, obviously dependent upon, so that will tell me how the signal propagates, which will also understand very clearly in my next lecture. And it depends upon the frequency. Obviously, if you change the frequency of the signal, your propagation velocity is going to be different, your attenuation is going to be different. That means the loss in the cable is going to be different, because these are all dependent upon the core equivalent set parameters of the this thing RLGC. So basically, this is the something, a very big concept which you understood, and now it will become very easy to understand various other parameters, which is characterized by a transmission line. And like it is like a 5 marks question, how to calculate the propagation constant in a transmission line. They are given you the value of R, L, G, C, and given the frequency, and that is a 5 to 7 marks question in a typical gate examination or any other examination, which is a transmission line is just very, very important concept. I think about 5-6 questions are there. So if you're thorough with my these lectures of next 10, 8 or 9 lectures which we have got, will be, and derivation, obviously, because the patterns are now MCQs type, understanding type, so derivation may not be asked for, but derivation is important to understand how actually I got this parameter. So yes, when we learn, we have to go for derivations. Otherwise, I would have given you the formula gamma is equal to R plus j omega and d plus omega c. And what I'm going to explain, the physical meaning, significance, you will not be appreciate that unless I would have derived. So with this, I stop it here because there is a new concept which we are going to start. Today, we talked about one parameter gamma. And I think from my next Monday, the hybrid classes are going to be there. So I'll be in the classroom. Today I am teaching from my office only, but from Monday, for your batch, the classes are going to be in hybrid mode. And from 18th, it will be totally offline mode. So at least for hybrid classes, many of you will be there, eager to come to the campus. I will also appreciate, because here we face so many problems. Like today, I will be able to use half of the screen of my iPad because of some static charge, I think. So there we should not have any problem. Will we have more interactive, more fun when we have one-to-one sessions? I am also eagerly waiting for meeting all of you, personally teaching you. And so you would have be also looking forward to come to DICT. So with this, I stop it here and we'll continue. There is a limitation because I have exhausted all 20 slides. There's some part on the upper part, there's some problem today. So, but anyway, this is the portion I wish to cover, and that is I covered, and we'll continue forward in my next lecture. Okay. So I stop it here. Any doubt before we close this session? 5 minutes to go. Okay, nothing in the chat box. So I will save this file, recorded file, as in this case. And I am happy with the performance in the part 2. As I told you, part 2 was MCQ type, which was set by me, more second on the FM and the PM and the noise. And it was a good performance, and it was auto correction. So there is nothing like there is wrong totaling or wrong this thing. It was auto corrected. It was result came out to you within few seconds of once you have logged out of your test. So, and it was a good performance in part 2, at least I could say. So we'll continue with that in the next lecture. So I stop it, my recording here, and end this.